Hello, welcome back to the playlist of topics on regression models and statistical machine learning. I'm Hemukumar Kasala, and as part of this video, we begin our journey on understanding multiple linear regression models with a detailed introduction. This is a very big topic comprising of many videos, and in this first video on introduction, we establish the need for a multiple regression model and explain the instances where this model is required over a single linear regression model. We learn about the structure of this model, its constituents, and their significance. We learn about the underlying assumptions that are essential to comply with in order to deploy this model. We learn more about the various possible forms of the predictor variables that constitute this model and their characteristics. Let's get into the video. As part of this lecture, we focus on getting introduced to the multiple linear regression models. We use single linear regression model as the basis to build our understanding on the multiple linear regression models. The simple linear regression model y equals alpha plus beta multiplied by x plus e describes the relationship between the dependent variable y and a single independent, also called as a predictor or an explanatory variable x. There are many situations wherein the simple linear regression model fails to describe the relationship between the dependent variable y and the independent variable x adequately, meaning does not establish a strong relationship between the dependent and the single independent variable. In such situations, including more predictor variables in the regression model reduces the uncertainty to a great extent, resulting in a more reliable and a useful model. For example, let's take the case of the house prices in any given city. Though the house size is one among the primary predictor variables, that alone does not adequately explain the variations across the house prices. Additional independent variables like number of bedrooms, baths, distance from schools, age, etc. account for a significant portion of the variation in the house prices as well. In this lecture, we extend the linear regression concepts to include two or more predictor variables, thus arriving at a multiple linear regression model. Interestingly, many of the concepts learned as part of the simple linear regression model applies as is or with little modification to multiple regression models. However, the computation of the coefficients and other statistical inferences are more complex than the simple linear regression model case. Like in the case of simple linear regression model, it is very rare that the independent variable y is related to multiple predictor variables x1, x2 and so on xk deterministically. That is, y is not a deterministic function of x1, x2 and so on xk. Therefore, a probabilistic model is widely a reality even as the number of predictor variables increases. A probabilistic model is arrived by adding a random error or deviation e to the deterministic function, as in y equals deterministic function of x1, x2 and so on xk plus e, in an identical manner like in the case of simple linear regression model. Thereby, we arrive at a general probabilistic additive multiple regression model that relates the dependent variable y to k independent variables x1, x2 and so on xk, as in y equals alpha plus beta 1 multiplied by x1 plus beta 2 multiplied by x2 plus and so on plus beta k multiplied by xk plus e, wherein the expression alpha plus beta 1 multiplied by x1 plus beta 2 multiplied by x2 plus and so on plus beta k multiplied by xk in the above equation is the deterministic function of x1, x2 and so on xk, and e is the random error. Beta i's in the model equation are the population regression coefficients, wherein each beta I can be interpreted as the change in the average value of the dependent variable y in the population for 1 unit change in the respective independent variable xi when values of all other predictor variables remain unchanged. The deterministic part, alpha plus beta 1 multiplied by x1 plus beta 2 multiplied by x2 plus and so on plus beta k multiplied by xk, in the model equation is called as a population regression function. The population regression function determines the average value of y for a given set of values of independent variables x1, x2 and so on xk. It is assumed that the random error E comply with the following requirements. That is, error E at any given values of predictor variables is normally distributed with mean value mu e equal to 0 and the standard deviation sigma e for the error remain constant for all possible values of predictor variables. That implies for any given value of independent variables x1i, x2i and so on xki in the population, the response y at I is normally distributed with mean value equal to the deterministic function of the xi's, which equals alpha plus beta 1 multiplied by x1i plus beta 2 multiplied by x2i plus and so on plus beta k multiplied by xki, and the standard deviation of y equals the standard deviation of error E, which equals sigma E, remains constant across all possible values of predictors. If the standard deviation of error sigma E is small, then any particular observed value y shall be closer to the mean value alpha plus beta 1 multiplied by x1i plus beta 2 multiplied by x2i plus and so on plus beta k multiplied by xki for any given value of the independent variables x1i, x2i and so on xki in the population. If sigma e is large, then the distribution of the observed values of y with respect to the mean value is significantly wider. Just to have a beginning level understanding of the deployment of a multiple regression model, let's take an example wherein y equals 1.4 plus 0.33 multiplied by x1 plus 0.16 multiplied by x2 plus e is the additive probabilistic multiple regression model, where y is the GPA score of a second year college student, x1 is the level of the student versus faculty interaction measured in a scale of 1 to 5, and x2 is the level of commitment to a major measured in a scale of 1 to 5. 1.4 is the intercept alpha, 0.33 and 0.16 are coefficients beta 1 and beta 2 respectively of the population regression function, and standard deviation of error E, sigma E, assumed to be known equals 0.15. Note, though the intercept alpha, coefficients beta 1 and beta 2 of the population regression function and standard deviation of error E, sigma E, are almost always unknown and they are often estimated using a sample. We'll learn very soon how to estimate the beta values using a sample, but here in this example we assume that we know these beta and sigma E values just for the sake of having a beginning level understanding on the use and the deployment of a multiple regression model. Let's use this population regression function and calculate the average or the mean GPA value for a chosen set of values for the independent, or in other words the predictor variables. For example, for students whose interaction level with faculty rated at 4.2 and level of commitment to their major rated at 2.1, the average or mean GPA is calculated using the population regression function. Accordingly, the mean value for y bar, equals the deterministic part of the population regression function, which is 1.4 plus 0.33 multiplied by 4.2 plus 0.16 multiplied by 2.1 equals 3.12. With sigma equals 0.15, 95% of the times an actual value for y, an actual GPA, can be found anywhere within the interval 3.12 minus 1.96 multiplied by 0.15 and 3.12 plus 1.96 multiplied by 0.15, which equals an interval between 2.826 and 3.414. Thus, like in the case of simple linear regression model, the multiple linear regression model provides a means to calculate the mean value for the dependent variable or the response variable given the values for the predictor or the independent variables. Having got introduced to the multiple linear regression models, we turn our attention towards the composition of the multiple linear regression models. We learn in detail about the various possible forms or derivatives or types that the predictor variables can take. The predictor variables in the multiple regression model need not always be another independent variable from the population. In certain situations, can be a function of another independent variable or variables. For instance, given that xk and xp are two different independent variables in the population, a predictor variable xi as in y equals alpha plus beta 1 multiplied by x1 plus and so on plus beta k multiplied by xk plus and so on plus beta p multiplied by xp plus beta I multiplied by xi plus error e can be a function of xk, for example, equal to xk square, or can be a function of xk and xp, for example, equals xk multiplied by xp. In general, one or more predictor variables in the multiple regression model can be a function of other predictor or independent variables from the population. For example, in y equals alpha plus beta 1 multiplied by x1 plus beta 2 multiplied by x2 plus beta 3 multiplied by x3 plus beta 4 multiplied by x4 plus e, x3 could be x2 square and x4 could be product of x1 and x2. Let's explore more on these special cases. A kth degree polynomial regression model as in y equals alpha plus beta 1 multiplied by x plus beta 2 multiplied by x square plus beta 3 multiplied by x cube plus and so on plus beta k multiplied by x raised to the power k plus e is a special case of a multiple regression model wherein x1 equals x, x2 equals x square and so on, and xk equals x raised to the power k. The more frequently deployed quadratic regression model where k equals 2 as in y equals alpha plus beta 1 multiplied by x plus beta 2 multiplied by x square plus e, and relatively less frequently deployed cubic regression model where k equals 3 as in y equals alpha plus beta 1 multiplied by x plus beta 2 multiplied by x square plus beta 3 multiplied by x cube plus e are a few polynomial regression fit cases that can be analyzed using the multiple regression model. Y equals alpha plus beta 1 multiplied by x1 plus beta 2 multiplied by x2 plus and so on plus beta k multiplied by xk plus e. Note the interpretation that beta I is the change in the average value of the dependent variable y in the population for 1 unit change in the respective independent variable xi when values of all other predictor variables remain unchanged is not valid in such multiple regression models that deploy polynomial regression fits. This is because 1 unit change in an independent variable xi cannot be achieved by keeping all other predictor variables unchanged, since the rest of the predictor variables are mathematical functions of the first independent variable. We just discussed a special case of a multiple regression model, which is a polynomial regression model as in y equals alpha plus beta 1 multiplied by x plus beta 2 multiplied by x square plus beta 3 multiplied by x cube plus and so on beta k multiplied by xk plus e. Now we learn about a special predictor variable which is called as an interaction variable. At times, change in the mean value of the independent variable y for one unit change in a predictor variable xi depend on the value of another independent variable xj. Then there is said to be an interaction between xi and xj, and such an interaction is modeled using another predictor variable which is the product of xi and xj, as in y equals alpha plus beta 1 multiplied by x1 plus beta 2 multiplied by x2 plus beta 3 multiplied by x1 multiplied by x2 plus e. When x1 and x2 interact with each other, the model that includes the interaction predictor x1 multiplied by x2 gives a much better fit than the one that does not include it. Beta 3 multiplied by x1 multiplied by x2 in the above model explains a good amount of variation in y, which otherwise, when not included in the model, shall remain unexplained by the model, resulting in a not very satisfactory model. There can be more than one interaction predictor included in a model. The maximum number of interaction predictors in a model depends on the number of independent variables that constitute the model and the number of possible interactions between them. An interaction predictor can be a product of more than two independent variables, for example x1 multiplied by x2 multiplied by x3, although in practice they are rare. It is very important to note that the interaction variables are identified primarily based on the knowledge in the problem domain, and the interactions are normally verified using selective scatter plots between the dependent and the independent variables. Let's understand the interaction variables with an example. Wind chill index is a very useful measure to indicate how cold it actually feels. Table below provides a sample of size 135 that gives the wind chill index for 15 different temperatures in Fahrenheit and for 9 different wind speeds in miles per hour. Temperature x1 and wind speed x2 are the independent variables, and the aim is to capture the relationship between the dependent variable wind chill index y and the independent variables using a multiple regression model. In order to understand the interaction, if any, between the independent variables, the temperature x1 and the wind speed x2, we draw the scatter plots to examine the same. We draw two scatter plots, one each between one of the two independent variables and the dependent variable wind chill index. 1. Wind chill index versus air temperature by choosing one wind speed from the sample at a time. 2. Wind chill index versus wind speed by choosing one air temperature from the sample at a time. Let's look into these scatter plots in detail and understand how they influence our choice of predictor variables one by one. The scatter plot between the wind chill index and the air temperature, plotted for different values of wind speed, show a linear relationship. However, the slope of the linear relationship differs with each value of the wind speed. Observe that they are not parallel to each other. That provides two insights into the relationship. Wind chill index shows a linear relationship with the air temperature, and the slope of the relationship is influenced by another independent variable, the wind speed. Therefore, the independent variables air temperature and the wind speed interact with each other. That provides a hint that the multiple regression model shall include two predictor variables. One, the air temperature x1, and an interaction predictor variable, that is the product of air temperature x1 and wind speed x2, that is x1 multiplied by x2. Now let's proceed to check the second scatter plot between the wind chill index and the other independent variable wind speed before concluding on the final model. The scatter plot between the wind chill index and the wind speed, plotted for different values of air temperature, show a nonlinear relationship. However, the nonlinearity is not the same with each value of the air temperature. In other words, air temperature influences the nonlinearity. The scatter plot provides two additional insights into the relationship. One, the wind chill index shows a nonlinear relationship with the wind speed, and two, confirms that the independent variable air temperature influences the nonlinearity. Therefore, wind speed and the air temperature interact with each other. From the two scatter plots, we understand that the multiple regression model shall include 1. The independent variable air temperature x1 to which the wind chill index is linearly related, and 2. The independent variable wind speed x2 to which the wind chill index is nonlinearly related, and an interaction variable that is the product of x1 and x2. Note that the independent variable wind speed x2 to which the wind chill index y is nonlinearly related needs a transformation such that y is linearly related to transformed x2, that is x2 dash, is included in the multiple regression model instead of x2. We discussed on these transformations during the lectures on polynomial regression and transformations. Since the nonlinear scatter plot curve between wind speed x2 and wind chill index y is similar to the one in quadrant 3, a useful transformation from the transformation table can be the one from the powers below no transformation in the table. Accordingly, x2 dash, that is transformed x2, is achieved by raising x2 to a power whose value is less than 1. Choosing x1 and x2 raised to the power 0.16 as x2 dash as the independent variables and x1 multiplied by x2 dash as the interaction variable, we arrive at an estimated multiple regression equation after feeding the sample data to any commonly deployed regression analysis software tool, as in y hat equals 35.74 plus 0.621 multiplied by x1 plus 35.751 multiplied by x2 dash plus 0.4275 multiplied by x1 multiplied by x2 dash. We use the term estimated multiple regression equation because we are estimating the model using a sample and not from the whole population. We will discuss on estimated model and its estimated coefficients soon in detail. In the above estimated regression function, y hat is the estimated response. The estimated intercept A equals 35.74 and the estimated slope coefficients B1 equals 0.621, B2 equals 35.751 and B3 equals 0.4275. This example helped us understand the concept of interaction between independent variables in a multiple regression model, and also the case where a transformation is applied on an independent variable, which exhibits a nonlinear relationship with a dependent variable. So far, we dealt with certain derived types of the predictor variables, namely polynomial and interactive, wherein these variables were derived from one or more predictor variables already present in the population. However, until now, the types of the predictor variables that we dealt with were quantitative or numerical in nature. It's time that we take a look at the need for incorporating the qualitative or categorical variables in addition to the quantitative variables into the model. Categorical variables, for example like sex, which can be either male or female, direction, which can be north, south, east or west, income groups, which can be low income, middle income or high income, or housing, which can be ocean facing with beachfront, ocean facing without beachfront, and not ocean facing, etc. However, we cannot incorporate these categorical variables into the regression model as it is with these enumerations. We first need to encode these categorical variables into numerical values. We need to carry out numerical encoding of categorical variables. Numerically encoded categorical variables are called as indicator variables or dummy variables. Numerical encoding depends on the type of the categorical variables. There are two types of categorical variables, and hence there are two different methods, one for each type. One, dichotomous, meaning two categories as in married or unmarried, local or imported, etc. And two, multiple categories, example, categories as just discussed under direction, income groups, housing, etc. Encoding a dichotomous variable is simple. For example, categorical variable marital status X can be encoded as 0 for unmarried and 1 for married. Similarly, employment status X can be encoded as 0 for unemployed and 1 for employed. A dichotomous variable which has two values is encoded using a single indicator variable. While value 1 represents one of the two categories, X equals 1 means married, value 0 represents otherwise. Otherwise in this case is X equals 0 means unmarried. Therefore, to encode two categorical values, we required a single dummy indicator variable. Extending this logic, a multiple value categorical variable is encoded using number of categories minus 1 indicator variables. For example, categorical variable direction that has 4 categorical values as in north, south, east and west requires 3 indicator variables x1, x2 and x3. x1 equals 1 means north, equals 0 means otherwise. x2 equals 1 means south, equals 0 means otherwise. x3 equals 1 means east, equals 0 means otherwise. And x1 equals x2 equals x3 equals 0 implies it is west. As can be seen above, the left out or the last categorical value west in this case is implied when all the above 3 indicator variables take the value 0. On the similar lines, the categorical variable income group that has 3 categorical values as in low income, middle income and high income requires 2 indicator variables x1 and x2. x1 equals 1 means high income, equals 0 means otherwise. x2 equals 1 means middle income, equals 0 means otherwise. And x1 equals x2 equals 0 implies it is low income. Let's understand the influence of the categorical variables in a multiple regression model using an example. Let's consider a multiple regression model y equals alpha plus beta 1 multiplied by x1 plus beta 2 multiplied by x2 plus e, where y is the writing competence score, a numerical variable, x1 gender, male or female, a categorical variable, equal to 0 if male, equal to 1 if female, and x2 perceived value of writing, a numerical variable. The regression equation which provides the average or the mean value y bar equals alpha plus beta 1 multiplied by x1 plus beta 2 multiplied by x2. Note, we have considered a regression model where the independent variables x1 and x2 do not interact. Substituting the two possible values for x1 equal to 0 and 1 in the regression equation, the mean value y bar, we have y bar equals alpha plus beta 1 multiplied by 0 plus beta 2 multiplied by x2, which equals alpha plus beta 2 multiplied by x2 when x1 equals 0, and y bar equals alpha plus beta 1 multiplied by 1 plus beta 2 multiplied by x2, which equals alpha plus beta 1 plus beta 2 multiplied by x2 where x1 equals 1. That shows the mean value y bar is more by a value beta 1, assuming beta 1 is positive, for female students where x1 equals 1 compared to male students where x1 equals 0 for a given perceived value of writing x2. Therefore, including a dichotomous categorical variable that does not interact with other independent variable or variables in a multiple regression model results in two regression equations whose mean values for a given set of values for the rest of the predictor variables differ by a fixed offset equal to the value of the coefficient, which is the beta coefficient, associated with that categorical variable. Note, it is sometimes possible that the gender dichotomous categorical variable x1 could be interacting with x2, the perceived value of writing, in which case the regression equation would be mean value y bar equals alpha plus beta 1 multiplied by x1 plus beta 2 multiplied by x2 plus beta 3 multiplied by x1 multiplied by x2. And substituting 0 and 1 for x1 in the above regression equation, we have mean value y bar equals alpha plus beta 1 multiplied by 0 plus beta 2 multiplied by x2 plus beta 3 multiplied by 0 multiplied by x2, which equals alpha plus beta 2 multiplied by x2, where x1 equals 0, and y bar equals alpha plus beta 1 multiplied by 1 plus beta 2 multiplied by x2 plus beta 3 multiplied by 1 multiplied by x2, which equals alpha plus beta 1 plus beta 2 plus beta 3 multiplied by x2, where x1 equals 1. The resulting regression line graphs are shown below. The difference in the mean values y bar for any given value of perceived value of writing x2 is determined not just by the difference in the intercept values alpha plus beta 1 versus alpha, but also by the difference in the slopes beta 1 plus beta 2 versus beta 2. Now we can summarize the learnings for a dichotomous categorical variable and a multiple value categorical variable. The number of indicator variables included in multiple regression model equals 2 minus 1, which is 1 in case of a single dichotomous categorical variable, while it is n minus 1 in case of a single multiple value categorical variable, where n equals the number of categories that the variable represent. The number of resulting regression equations from a multiple regression model equals 2 when the model includes a single dichotomous categorical variable, and equals n when the model includes a single multiple value categorical variable, where n is the number of categories comprised in that variable, of which one regression equation is without any indicator variable, representing the regression equation for the default category, and each one of the remaining n-1 regression equations include one indicator variable from the n-1 dummy indicator variables. When the categorical variable does not interact with the rest of the predictor variables, the difference in the mean values of y for any given set of values for the rest of the predictor variables equals the fixed value beta I in case of a single dichotomous categorical variable, where beta I is the coefficient of the resulting single indicator variable. And equals beta x, again a fixed value, between each of the n-1 regression equations with one indicator variable and the default regression equation without any indicator variable, where beta x is the coefficient of that indicator variable in the respective regression equation. When the categorical variable does interact with any or few of the rest of the predictor variables, the difference in the mean values of y for any given set of values for the rest of the predictor variables is not fixed. In other words, it's not a constant. This is because the individual beta x coefficients of the remaining predictor variables in each of the n regression equations are not the same. They are modified because of the interaction with the categorical variable. That brings us to the end of the discussion on Introduction to Multiple Linear Regression Models. See you back soon with the next lectures on this topic on multiple linear regression models. Bye for now.